welcome to our factory. Today, I'll show you exactly how railway tracks are made step by step. Don't forget to subscribe for more behind-the-scenes videos like this.
Every year, millions of cars reach the end of their lives, leaving workers to manage mountains of steel left behind.
One car weighs over a ton. Multiply that by millions, and the scale quickly overwhelms both land and resources.
Workers focus on what matters most, the high-strength steel hidden beneath paint, plastic, and upholstery. Without intervention, these vehicles slowly leak chemicals that workers must contain before they reach soil and water.
Steel can be melted and reused endlessly, but only through precise human control and industrial expertise.
The same hands that process scrap steel help build the rails that move entire economies forward. Before steel is reborn, workers must safely dismantle every vehicle piece by piece.
Every car begins here, they say. Iron ore mined from the earth, extracted by workers using some of the largest machines on the planet.
Inside steel mills, workers remove oxygen from iron ore, transforming raw rock into molten steel through controlled chemical reactions.
By adjusting carbon and alloy content, engineers tune steel for strength, flexibility, and crash resistance.
That steel is rolled, stamped, and shaped by workers into frames designed to absorb energy and protect lives.
After years of vibration, weather, and impact, steel weakens, but its core structure remains reusable.
Not all car steel is the same. Frames, panels, and engines use different alloys for specific mechanical roles.
That diversity makes car steel extremely valuable, a ready-made supply of high-quality industrial material.
Before recycling can begin, every car must be carefully dismantled to separate steel from everything else. Before machines take over, workers inspect every car to identify hazards and plan safe dismantling.
Fluids like fuel, oil, and coolant must be removed first to prevent fires, explosions, and environmental contamination. Batteries and airbags store energy long after a car stops driving, making them serious safety risks.
Electronics contain copper, rare metals, and toxic substances that must be separated before shredding.
And some steps require human precision, while others are handled by automated systems built for speed and consistency. Non-metal parts are removed to ensure clean steel recovery and protect downstream recycling machines.
This stage prioritizes safety over speed, reducing accidents and protecting both workers and equipment.
Once stripped and secured, these steel shells are finally ready for the most violent stage of recycling.
Once stripped, steel shells are fed into shredders designed to break entire cars apart in seconds.
Operators carefully control speed and load to prevent jams, damage, or dangerous mechanical failure.
Cars enter the shredder slowly, ensuring the machine breaks metal efficiently instead of violently rejecting it.
Inside, rotating steel hammers strike thousands of times per minute, fracturing metal through sheer kinetic energy.
Shredding increases surface area, making it easier to separate materials and remove contaminants later. The forces involved are so extreme that shredders require constant inspection and heavy maintenance.
Engineers balance energy use with throughput to keep recycling efficient and economically viable.
What exits the shredder looks chaotic, but it's perfectly prepared for precise material separation.
After shredding, the mixture looks chaotic, but every fragment is now sized for precise separation.
Powerful magnets instantly pull steel away, using its natural magnetic properties to separate it from waste.
This step relies on basic physics, not guesswork, allowing engineers to control purity with precision.
Eddy currents push non-magnetic metals away, preventing aluminum from contaminating steel.
Airflow systems remove plastics and fibers, separating materials by weight instead of chemistry.
Despite automation, human inspection ensures steel meets strict purity requirements. Even small impurities can weaken future rails, making this stage critical to safety.
Only after careful separation is the steel ready to be melted and reborn.
This is where recycled steel is reborn, inside furnaces hot enough to melt solid metal into liquid.
Electric arc furnaces are ideal for recycling, using electricity to melt steel efficiently and precisely.
Powerful electric arcs generate extreme heat, breaking down solid steel into molten metal.
Engineers adjust carbon and alloy levels to control strength, hardness, and flexibility.
Impurities rise to the surface as slag, allowing workers to remove elements that weaken steel. Samples are tested in real time to ensure chemistry meets strict railway standards.
Despite automation, final decisions still rely on human expertise and experience.
With chemistry perfected, the molten steel is ready to be shaped into railway rails. Molten steel is first solidified in controlled molds, forming long slabs designed for precise shaping.
Continuous casting reduces internal defects, ensuring rails have uniform strength from end to end.
Before shaping, steel is reheated to restore flexibility without weakening its internal structure.
Massive rollers gradually squeeze the steel, shaping it without cracking or introducing stress.
Each rail profile is engineered to spread weight evenly and resist constant vibration.
Rails cool slowly to prevent internal cracks that could cause future failures. Even with automation, human oversight ensures consistency and safety at every step. At this stage, recycled steel has become fully formed railway track material.
Railway tracks carry enormous loads, so every rail must be proven safe before installation.
Ultrasonic waves reveal internal cracks invisible to the human eye.
Even microscopic flaws can grow under repeated stress, leading to catastrophic rail failure.
Rails are deliberately bent to confirm they flex without cracking.
Fatigue tests simulate millions of train passes in just a few days.
Heat treatment is verified to ensure rails resist wear and deformation.
Despite advanced machines, final approval still comes from experienced human inspectors.
Only rails that pass every test are cleared for transport and installation.
Before shipping, rails are cut to exact lengths to match railway design standards. Protective coatings reduce corrosion during storage and transport.
Rails are loaded carefully to prevent bending or surface damage.
Most rails travel hundreds of kilometers before reaching construction sites.
Once delivered, installation crews take over the process.
Alignment must be precise to prevent vibration, wear, and derailment.
Rails are locked into place to handle constant dynamic loads. Once installed, recycled steel immediately returns to service.
And that's how old cars are recycled into railway tracks from start to finish.